And Mandar sir, good evening, first of all.
Good evening.
Good evening, sir. Sir, can we start the session?
Yes, we can start.
Yes, sir. Radhika ma'am, over to you.
Yes, madam. A very warm and pleasant evening to one and all present here. I, Mrs. Radhika Pazare, on behalf of Information Technology Department at AC Patil College of Engineering, Kharghar, welcomes Dr. Pramod Maske sir and his teammate, Mr. Mandar Gurav sir, to the ATAL FDP Next Gen Computing Advances in HPC and Quantum Technologies for Data-Driven Insights. It is an absolute privilege to introduce a remarkable individual who embodies innovation, expertise, and dedication to both technology and education. Please join me in welcoming Dr. Pramod Maske sir and his teammate Mr. Mandar Gurav sir. Pramod sir is the Senior Project Manager for the Maharashtra Drone Mission at the prestigious Department of Aerospace Engineering, Indian Institute of Technology, Bombay. Dr. Pramod brings with him over 2 decades of rich and diverse experience in product development, training and project management, and consulting, having worked on numerous large-scale government and private embedded system projects. His contributions have made a significant impact not only in advancing technology but also in nurturing the next generation of innovators. At IIT Bombay and other institutions, Dr. Pramod has been instrumental in developing training centers and laboratory facilities, creating learning environments that inspire innovation. One of his standout achievements is holding a patent for an energy meter adopted by the Government of India to comply with Kyoto Protocol norms, which is a testament to his commitment to a sustainable technology. In the field of academics, Dr. Pramod has developed a comprehensive course on embedded product design and IoT, offering a hands-on approach for working professionals and engineering graduates. He has designed a training module on embedded supercomputing using NVIDIA's GPU-based Jetson platform. Furthermore, he has guided numerous final year engineering projects across college in Mumbai and Pune, shaping the minds of future engineers. Beyond academics, his product innovations stand out as exemplary contribution to the engineering landscape. Some of his major achievements includes the design and development of GSM-based compact energy meter for the Bureau of Energy Efficiency under the Ministry of Power, the creation of an IoT-based ultrasonic water meter for the Ministry of Drinking Water and Sanitization, development of a DC motor control kit and magnetic leviation system simulator under the Virtual Labs initiative by the Ministry of Human Resource Development, engineering a GPRS-based wireless LED display system for an Indian railway, and designing numerous industrial instruments that have been widely adopted across various sectors. Today, Dr. Pramod continues to manage impactful projects and guide project staff and interns at IIT Bombay, championing cutting-edge development in embedded system and product design. It is indeed a rare opportunity to hear from someone whose contributions span across such a diverse area of disciplines. Let us give a warm welcome to Dr. Pramod Maske sir and his teammate, Mr. Mandar Gurav sir, as they share their invaluable insights and experience with us today.
Thank you very much, madam.
Sir, please accept our virtual token of respect.
Thank you very much. Nice idea. Okay.
Now I request Dr. Pramod Maske sir to start the occasion. Over to you, sir.
Yes. Thank you very much. You forgot to introduce me one more thing, that I am an alumni of AC Patil College.
Oh,
And
Yes, sir. Yes.
that's nice to hear,
yeah,
sir.
no, not forgotten. I proudly say that I am an alumni of AC Patil College. Okay. So, today we'll be talking about high performance computing. Let me present my slides. May I, madam? Yeah.
Yes, sir. Yes. Sir, you can share your presentation now. I have stopped my screen.
Yes. Yes. I'll do it. Is it visible?
Yes, sir.
Yes.
Yes, sir.
As hello everyone. Uh, I think we are sitting for lectures in the evening. Uh, Today I'll be talking about data-driven insights using HPC. So HPC is a very common word nowadays that we understand high performance computing. But today I'll be talking about a little bit different approach of HPC, how it is used for decision making, and I'll like to go before a little bit of HPC, that where HPC is used. As I'm from IoT background, I know that putting different nodes and putting different intelligent nodes in the society or in industry is generating large amount of data which which is uh, which is carrying some important information, and sometimes data may not carry some important information. We generate lot of useful data as well as we generate lot of unuseful data. So how to tackle this? Because there is an explosion of data. Different sensors are generating different data. In case of IoT, if you go for some simulations, if you go for some monitoring some plant industry, it will be also generating some large amount of data. It can be useful or it can be noisy data. First of all, we need to understand how to separate out useful data from non-useful data. For that, we need to apply some strategies, and this has to be done on real time. This has to be done on real time so that we can produce results to the users as early as possible than data is generated. This instant analysis of data, instant processing of data is generating some high computation needs. We need to understand, process, solve lot of equations, and generate useful information for the user. Industry is going at its own pace. Now it is role of our educators to cope up with that speed so that our next generation will be ready to handle this kind of challenges. If you see the challenges, there are two types of challenges: challenges put forward to machines and challenges put forward to students or educators. Challenges put for machines is how I can have a more powerful machine, more powerful computer, so that it can generate this kind of data instantaneously. If I want to run some simulations, how I can get results very fast. For that, we require more powerful machines which can generate faster and more accurate insights. Also, there are another challenge is how to create our next generation, how to show our students that what is coming forward to them by giving right infrastructure at the college level itself. We need to have our infrastructure ready for students. We need to integrate advanced tools right now in their curriculum, and this will be able to do only by having more awareness of high performance computing. I'm trying to justify that why we require high performance computing right now. Time has already come. What we can do with high performance computing? From engineering background, if you see, if somebody is from mechanical background, he will understand that right from nanostructures to big structures, I need to calculate behavior of structure exposed to different environmental conditions. I need to see the performance of the strength of the structure when it put forward to different stress and strains. I need to know the analysis. There are traditional methods uh, by putting formulas and algorithms to calculate this, but that might take long time to come up with the results. If I'm talking about fluid dynamics nowadays, we think that fluid dynamics is only used for water flowing through a pipe. I need to model that. But right now it is very important question, important or I will say complex problem, that we need to model the flow of water. If I'm trying to give water supply to big cities, I need to have model of the cities, how a demand created at one particular place, or demand created at one particular ward, can disturb the water supply at other sections. So only knowing fluid dynamics and doing it traditionally may not be sufficient nowadays. I need to manage my water supply network dynamically. That means right now what we do, we plan for certain certain load, and we provide a network, pipelines and walls and everything, and then it is static. We cannot operate it dynamically as the demand increases or some disturbances. My high performance computing can take decisions on the go and can modify the distribution of water. I'm just giving one example of fluid dynamics. Another thing is, if I'm looking at material science, there is a lot of research is going on in material science, and to understand properties of material, how that material is behaving under certain conditions, I need to know the behavior of material, and I need to put it in front of my, I need to put in form of some equations and algorithms, and do do computation, which might take long amount of time. That's why again there is a need of HPC, I can say. Energy system, if I'm having a distribution network of electricity and there is some disturbance at one area, I need to cope up with that disturbance. If there is a requirement of energy at particular area, I need to cope up with that requirement without disturbing other area. How it is possible on the go? How it is possible dynamically? Only by providing high computing facility to my traditional systems. So what is our role? Today we'll be talking about HPC in detail. I'm just trying to uh, start the topic by understanding what is our role. Our role is, whatever is happening in industry, we need to introduce that to our students. We are already doing it. No doubt we are already doing it. We need to put focus more on HPC related research and teaching. We need to inspire our students to take this as a career for data driven industry, and for that we need to tell them that what is important. One thing is how data is generated, another thing is after data is generated, how to analyze, how to do analysis, how, if somebody wants visualization of data, how to put it into visualization. Again, I'm saying that it has to be done quickly, it has to be done online. For that we need to understand HPC fundamentals and applications and use proper tools to provide data and analysis of data on the time. So what we'll be talking today will be understanding what is HPC. Will be understanding what is role of HPC in engineering. We'll see some examples. We'll see some case studies, and we'll also focus on some opportunities where we can do our research, what are the challenges. We'll be talking about this in our talk today. So as we know what is HPC, HPC is giving very high power computational power to our day-to-day problems, where data is large. New sensors are generating a lot of data. We need to filter out the data. We need to understand, and we need to create picture of. We need to create actual picture of the environment using our data. For that, we need to do a lot of calculations quickly. We need to solve a lot of algorithms very quickly. And for doing this, we need, of course, we need parallel processing. We cannot do this with single thread machines like our normal CPU machines. We might have to use GPUs. We might have to use multiple threads, multiple computers. We call it a supercomputer. And we need to have tools ready for generating real-time data and analysis of real-time data. Of course, by doing this, we'll see a lot of impact. Already we have started seeing that our designs are coming better. Look at the simulations, aerospace related designs. We are designing much better than earlier, and it has percolated to our car designs also. Now you can see a lot of simulations, what are a lot of testings in real time, and we can do design optimization. Our turnaround time has reduced. For renewable energy solutions, we can predict our environment better, and we can predict that when the energy requirement will be more from non-renewable sources, and where I can use renewable sources. Of course, not the less that smart cities. Now we have started seeing government is funding a lot of to smart cities. Why? Because it is not only for fancy, it is giving me a lot of useful data. It is helping me to understand the behavior of large crowd, behavior of user demands, and we can plan better, and we can handle emergency situations in better way if I have sensor network throughout my cities. And all this is possible by having very high performance computing in background. So what are our strategies? What we'll have to do? We'll have to, of course, we have started, as I said, we have to introduce more modern tools of HPC in our syllabus itself. We need to have more collaboration with industry, and we need to have real world problems in our projects, college projects. What benefits students will get is they will at least have an exposure of the future, what they are going to face when they go out of the college. They will develop a skills of real world problem solving than academic problems. Basically we are making them ready for the future, I can say. And this will not go west. Definitely they will have a lot of opportunities in India, abroad. They will have lot of they will be having a lot of problems, and they will explore different problems, and definitely they will get rewards for that. They will be placed at very good positions in industry. For that what we need to do right now is these are the challenges to get HPC resources in our colleges, our education systems, or we need to have maybe a centralized share resource for different colleges. uh, a big institute can take a lead and make this HPC resources available on a sharing basis to different colleges. And we can always call industry experts and show them that now we have a facility at our end. You can give us real world problem, we'll simulate it over here, and we can help you to solve your real world problems. Okay. And this is the way we'll move ahead. This is the way we'll move ahead, by solving real world problems. Now this is just about what is going to do, what we should do in HPC. Understanding more about HPC, how it is actually, how the resources are actually generated, how we can solve real world problems, what are different case studies. I'm giving control to my colleague Mandar Gurav. He is a expert in HPC. He is from Computer Science Department, IIT Bombay. He will be presenting some case studies and more insights about this in my next part of the lecture. Mandar, over to you.
Yeah, thank you, sir. So,
I'll stop sharing.
yes, I'm sharing now. Sir, can you confirm if my screen is visible?
Yes, sir. Yes, sir.
Yes, sir.
Yes,
Yes, sir.
ma'am.
It is
Okay.
visible.
Okay. Yes. Yes. Thank you. So, good evening, all. So, I'm sure it's very late evening, and probably everybody is not very much used to attend late evening sessions. That too, probably a lot of technical jargon is being discussed. Okay, so I'll try to keep it little light. Okay, so just to continue from where Sir stopped. So the thing is, Sir already talked about different aspects. I would say he covered a broader umbrella under which I can specifically focus on the storage from the HPC point, and how a lot of this data which is sitting onto the storage device in the HPC can be actually used for some very interesting problems. Okay, so just to make it very interesting, I picked some of the use cases which are very specific and very interesting to wide audience, rather than taking some a typical computer science kind of applications. Okay, so to begin with, we have already seen in today's world, data is the currency, or money, right? So if you have a a billion-dollar startup or unicorn, as they say, and even if you are burning crores of rupees a month, okay, but you have a huge amount of data regarding your customers and stuff like that, probably people are willing to give you more and more investments just to keep you running, so that at some point of time you will make profit out of it. Worst case, whatever data you have, that's a lot more valuable than kind of cash that you are burning, right? So we are in that particular world. Again, we know we are in AI age, right? So we're collecting and storing the data, and especially whenever you go to websites like Amazon and Myntra and whatever, every click matters, right? So if you click on certain things, if you click on some other things, so then there are these recommender systems which are trying to analyze how you are browsing through different products, and accordingly they're recommending you better and better such solutions or products to buy from, right? So that's why collecting and storing the data for future consumption is very important. And especially if you look at a lot of these organization, except Amazon and things like that, probably a lot of the traditional businesses, they don't really care too much of data, right? So they will just store some basic stuff, because they don't want to spend a lot of money in storing the data and stuff like that. But now today people are trying to find out what are the different business insights which were completely invisible, so to say, a few years ago. So now you can look at your data and find out some interesting patterns into your data, and figure out what kind of customers are buying your products, and stuff like that. What are their demographics, age, and so many different things, right? So now probably you might also have seen if I want to market my product, I can always go and have a a large traditional advertisements. But instead, I can do these things based on very specific targeted Facebook ads, Google ads and stuff like that, right? So that's where a lot of this value from data also comes in. Okay, and not to mention about the AI, because if you want to train your systems, you need a huge amount of data, right? So that's why you want to collect as much as possible and try to store as much as possible, right? So if you go back 5-10 years ago, probably nobody cared too much about collecting and storing a lot of data. Certainly they collected some data, but that was very specific and very limited, which they feel is the important part. Rest they used to just throw away. Nowadays it's other way around, people are trying to see what kind of data they can collect, and they are just collecting it, and they are trying to say, okay, so we'll see what inside we gain from it. Okay, but let's start collecting the data, because without data I don't have the insights, right? So that's another key problem today. Okay, uh, apart from that, when we see there are traditional data intensive applications, okay, which have been people have been doing it, sir also mentioned about a couple of interesting use cases. Okay, but now, as I was mentioning, large number of businesses, even though they may or may not be using AI, or they may or may not be doing some analysis of data today, but they are gathering it and storing it, because they know future somewhere in the down the line, that data is going to give them a lot of very interesting insights, and that will add a lot of business value to their enterprise, right? So that's the reason a lot of people are gathering and storing all this data. So if you look at a traditional HPC system, okay, and even today's data center, okay, so there are different components. One is compute, one is networking, and third one is storage, right? And as we generally know, HPC systems are computing systems. Okay, we don't really say they are systems where we store the data. Okay, so when I learned my information sciences and those kind of subjects during my bachelor's, yeah, that time we used to have these courses from EMC Square. So those courses purely used to talk about okay, how do we store it redundantly, okay, disaster recovery site, and those kind of things, right? So people never really said okay, so there is this HPC machine and there are important component apart from the computing, or the processors or the GPUs things, right? So as I was saying, the most emphasis is given towards the computational power of the machine than the storage. Okay, and not to mention the efficient retrieval, and we will have a detailed discussion on that. Okay, so if you look at any HP system architecture, I just borrowed this particular image from NSM, National Supercomputing Mission website. Okay, so this is the architecture of latest Param supercomputer. It's called as Param Rudra, hosted at IUSC. It's in Delhi. Okay, so if you see broadly, there are three components, right? One is this compute nodes. So there are large number of compute nodes. Then there is this network, which is the backbone, and there are different types of networks, so to say. Okay, and then there is a storage. Okay, so if you see a typical HPC job, what I do is I run a HPC simulation or HPC job on these compute nodes. Okay, and I know that my data is stored somewhere in the system. Okay, but certainly the data is not stored on the same compute server where I'm actually processing it. There is a centralized storage somewhere in the system which is connected with high bandwidth link. But if you look at the rate at which the computational power has grown, okay, that rate is phenomenal, and the network as well as the storage system cannot keep up with that rate. So the thing is if you go back 5, 10, 20 years before, the kind of computational power we had versus the kind of network bandwidth we had versus the kind of storage and storage retrieval rates we had, that was completely different. The ratios were completely different than today. So today we are into a scenario where there is huge amount of compute power, but amount of storage is very limited. At the same time, the retrieval, so IO operations per second, which I can do on my storage, is very limited as compared to the computational power I have. So it's very easy to just stack up bunch of large number of servers, and we just say that okay, we have built a really large machine. Okay, so building that kind of really large machine is very easy. But when you want to build a balanced machine, what you need is you need a computational power, but you need to have the network which can enable all these computational servers to communicate efficiently with each other with sufficient bandwidth. At the same time, when I'm trying to work on certain applications, when I'm loading some data from my disk, which is probably storing petabytes and exabytes of data. Okay, in that scenario, how much I'm able to pull in from the storage and process it is also very important. Okay, so as a component, computational power, you can linearly scale. You can just keep on adding lot and lot of number of servers, but relatively your network cannot easily scale. At the same time, your storage can also be not very scalable. Okay, when you go and look at a lot of this marketing material from storage OEMs, they will say certainly, okay, so it's scalable and the exascaler and this and that, they will have fancy names. But trust me, when you look at really large machine and kind of data they are working on, okay, uh, traditionally the storage systems may not be able to keep up with kind of demand that these computational systems are trying to put up. Okay, and there are good number of benchmarks available and stuff like that. If you are interested, you can explore that. But I just wanted to give you a broad idea that hey, building a HPC machine with lots of compute power is very easy. Okay, what is hard is building a scalable network. Okay, having really high speed network to feed the data to the compute devices, and when they are communicate with each other. Okay, they should be easily share the data, which should be extremely fast as well as with minimum latency. And third challenge is the storage. Okay, so you can have really high performance storage. Okay, but it will be too expensive. You'll have a really high capacity storage, but it will be too slow. Okay, so I have a slide towards the end, okay, which talks about these things. But the thing is, when you build this kind of machines, a lot of interesting things are happening. Okay, so today we will not be spending too much time on that, but I have shared some of the links towards the end of the presentation, so you can take a look. Okay, so what's happening in that thing, but I'll broadly give you the idea. But before that, our main focus is the data driven HPC. So I'll just give you some interesting use cases. Okay, briefly talk through it, and then I'll talk about one of the project which is relevant to today's topic, which I worked for for one of the OEMs. Okay, let's get started with first examples. I think everybody knows CERN, or at least Large Hadron Collider, as it's called as. Okay, so you must have seen a lot of videos and photographs and a lot of talks about these devices, right? It's a very large device spanning over 27 kilometers as a circumference. So it's a tunnel underground, and so there are these particles which are accelerated, and then it will crash onto something, and it will it's so they are experimenting with this kind of things. So point is the particles are traveling at extremely fast velocities, and there are sensors all across these devices at various places, and it's collecting huge amount of data. Okay, so point is you can always collect the data, okay, at the sensors, but getting the data and storing it to the storage devices is altogether different story. Okay, so as sir mentioned, there are this lot of IoT devices, and today if you see large number of this industrial complexes, they will have huge number of sensors collecting all sorts of data and combining to get some insights into their business. But this is one of a kind experiment run by consortium of different countries, funded across different countries, and it's going to solve some of the very important basic science problems of our generation, right? So here they are collecting the data. Okay, but now you have to so it's a raw data, you have to filter it, you have to post process it, and then only you can store it. So the collecting is probably easy, but storing it will be very difficult, okay, relatively. And third thing, but the most important thing is now reading the data again and processing it so that we find out insights into that data is the key challenge. Okay, so so if you see they are collecting, so there are 150 million sensors, okay, which are collecting this data, okay, and they are collecting at 40 million times per second, okay. So you can imagine the kind of activity that is happening there, and per second it's generating 1 petabytes of data, okay. So generally, typically people have terabytes of storage, okay. So here we are generating 1 petabyte of data per second, okay. So when you actually collect the data, as I was saying, there are different things, different observations you have to perform on that particular data, right? So there are bunch of things that they already mentioned, so momentum of the tracks and origin, the energy, and so on and so forth. Okay, so probably if you are interested, I have given the links. You can take a look at this thing. But the thing is, this experiment, whatever we perform, okay, so it's happening in extremely small time scales, okay. At the same time, okay, we are generating huge amount of data, and until and unless I go and process the data, I cannot get anything about the experiment, okay. I know experiment is over, okay, that's the only thing I know. But whatever experiment happened, until unless I go and analyze the data, I won't be able to find out anything about the experiment. So it's just that some event has happened, some experiment has happened, but until unless that data is collected, stored, and then processed, okay, you will not be able to get some insights into what actually experiment happened, how things happened, and what exactly are the key results of the experiment. That is only available to us only after processing the data, okay. So this kind of so I know I picked the extreme example, but these are very interesting problems that people are working on, and these are massive data sets people are actually working on. And if you go and find out their computational infrastructure and how they are sharing the data with at different sites and processing it, that's phenomenal. So I don't want to get into specific project, but I just wanted to give you one use case, okay. So let me jump to the second use case, which is also similarish, okay, and probably a lot of the people might know, especially in Pune region, okay, or at least in Maharashtra region, people might know this thing called a GMRT, right? So there is this thing called as giant meter wave radio telescope. Okay, so it's near Narayangao, and if you pass through that patch, probably you can see the actual dish, okay, just next to your road, right? So similar, a new telescope, radio telescope is being built, but this is not a only telescope at a specific location. It is spread across the world at different location, and there are like huge number of dish antennas which are collecting this data. Okay, so name of this project is Square Kilometer Array, and India is also part of this particular project. So, and a lot of GMRT people are also contributing, and I think as a country we are also contributing financially to this project. Okay, so this is like an artist's impression, but there are actually this is the latest slide which I borrowed from this link. So there are these two sites. One is in Australia and one is in so this is in Australia and this is in South Africa. Okay, there are like two different types of things. So here there is one dish kind of architecture where there are about a total 197 dishes, and this is antenna kind of architecture where they have about 131,000 antennas, right? And they receive at certain frequency and so on and so forth. Okay, but if you look at the scale or the area over which this thing is spread is so the largest distance between the two antennas or dishes is about 150 kilometers, and here it's 65 kilometers, right? So this is spread over large area, so that's why it acts as a giant telescope. Okay, even though it's collection of smaller number of large number of antennas or dishes, it acts as a much larger telescope. So now the thing is, the problem here is again the amount of data. So for example, if you see this particular site, okay, the data transfer rate here is 8.8 terabits per second, which is I think reasonable as compared to previous slide, but still it's pretty high. And on this side, this is 7.2 terabits per second. Okay, so the thing is the life of these two particular projects. One is SCA and the LHC. It's very different. So LHC, they conduct experiments. Okay, it's not running continuously generating the data. Whereas if you look at these radiotelescopes, their lives are in tens in decades, and continuously they are collecting a lot of the data. Okay, so collecting that data, and again, as I mentioned previously, processing that data is a challenge. Okay, so just wanted to give you a brief idea about what kind of large projects actually use HPC, and what kind of data rates that they typically have. Okay, so that's what I was talking about. So one the antenna thing gets 7.2 Tbps data, and the other one gets 8.8 Tbps. So they have this architecture where they receive the data, then it goes to a signal process. So essentially these are all radio signals. So first they will filter out or whatever, they have multiple steps. So just to process the signals, okay, which gives you the actual data which we can further go and process it. So that will be given to the science data processor. And in general, if you look at it stores about 600 petabytes of data per year. Again, researchers can go and retrieve that data and do their own modeling and further processing of the data. But generally, they are planning to store 600 petabytes per year. Okay, which is very massive. Looking at the time scales of this particular project, so they will run in decades. Okay, so probably you'll have huge amount of data coming in, or maybe I'm not sure, but in future they'll start collecting more and more signals from different frequency bands to collect more data to find out distant galaxies and stuff like that, right? So this is, in my opinion, this is the smallest or minimum amount of data which is going to get collected. But probably as they upgrade their infrastructure to receive the data and store the data, probably they might even increase these numbers. Okay, yeah. So these are the two extremely large scale I would rather say extreme examples I just wanted to briefly mention about and why that is important. Okay, then I'll just give you a simple real life use case for real life applications. Okay, so this is a very simple yet very complex simulation for Mars lander. Okay, done by NASA, and this was the actual demoed in NVIDIA's supercomputing conference. So the CEO had this simulation done in real time on the stage. Okay, just to demonstrate it. Okay, so it was an actual real life simulation done for the real life design with the real life measurements for this particular lander, which was supposed to be a land in I think 2030 or something, right? So there is this code called as Fun3D code, which is a CFD code which simulates this thing. Okay, so it generated about 150 TB of data, and this simulation was done for this 150 TB of data. Okay, only for the landing part, not the full simulation, but the landing part. And you see this, which has millions of particles which are being simulated in real time. Okay, so they used 4 NVIDIA DGX2 box, which was streaming the data from the storage device at 400 Gbps. Okay, so which is extremely high. So when you have 4 NVIDIA DGX, and typically DGX will have 8 GPUs, so we can think of at least 4 or 8 GPU configuration. So 16 to 32 GPUs are kind of consuming 400 Gbps of data to volume render this particular thing. Okay, the simulation was already done. This is just to render it, and so that scientists can visualize and figure out the scientific things about this particular simulation. Okay, so they use this NVIDIA Magnum IO. So I'll briefly talk about what it does. Okay, and they use NVIDIA Index to store the data in unstructured format. Okay, so the key point here is this NVIDIA Magnum IO. which uses GPU direct storage. So what is the GPU direct storage? So traditionally, what happens is when I have a GPU and I have CPU with its memory, and I have this network interface card, okay, which is connected to like some remote disk, okay, some storage device. So when I want to actually access something on the GPU, which is not available in my memory, which is stored in some remote storage device, what I do is essentially I go and fetch that particular data, okay, via my memory, right? So in my main memory, I don't have the copy. So first I have to go and fetch that data to my CPU's main memory. Okay, from CPU's main memory, I'll copy it to the GPU memory. So my GPU, when it wants to access something which is not available on the same system, on a remote system or a storage device somewhere available over the network, what I would do is like I'll first go and put up the request. That thing will be copied to like my CPU memory, and then it will be copied to GPU memory, and then I will be able to access it. Okay, so it has like a lot of overheads, and it adds like a lot of latencies. Also, this path becomes like bottleneck, and it also slows down the data transfer speeds and so on. So what NVIDIA has done is like they have built this thing called as Magnum IO software stack, which internally uses GPU direct storage. So what it does is like when GPU wants to access anything which is not sitting on the network, which is not sitting on this my main memory, okay, on the same machine, which is sitting on my network somewhere. So what my GPU can do is it can just put up a request to the disk directly without actually interfering the CPU. So it has multiple benefits. One is like okay, so you save on bandwidth and latency. Second benefit is you don't have to bother the CPU to do the transfer. See, the thing is when you are transferring this data back and forth, unless you have a NIC which is like which supports the offload and advanced capabilities, the CPU is going to get involved into this particular operation. Okay, with GPU Direct, you are not really bothering CPU. So all your CPU cores are always available for the computations that you are doing on the CPU side. Okay. So in today's world, like, disturbing CPU for processing the DMA request, or even like, processing the packet processing stack or network stack is very expensive, and it adds a lot of noise into the system. And when I'm running large number of processes or threads on really large machine, okay, it might slow down my scalability thing, right? So what I want to do is I don't want to disturb the CPU. At the same time, I want to access it as quickly as possible. So what they have done is like they have built this GPU direct storage technology where you can just go and talk to the storage device without really bothering the CPU. Okay, and that's the key thing which is driving a lot of the innovation today, because all your massive data which your GPU is going to consume is sitting onto the storage device. Okay, so you don't want to first load it in main memory and then give it to the GPU. GPU can just go and access it wherever it's available. Okay, so that's the key idea behind this GPU storage. Okay, so I don't want to miss out the key part, so that's why I added one more slide for AI. Okay, so I'm not an AI expert, but because now, as everybody is aware, like AI needs data, and because you need like a huge amount of data, the storage is the key part of whole system. Okay, so even though people only talk about the GPUs because GPUs are very important in model training, equally important is your storage. If you don't have enough network bandwidth, and if you don't have enough IO operations available for your storage device, then you are not going to feed your GPUs and like efficiently run them. Okay, so GPUs will be always waiting for the data to come in, and then like you'll process it. Okay, so when people talk about like having 4,000, 10,000, or whatever, like 1 lakh number of GPUs, they need to have like really impressive network connectivity. At the same time, they need to have really huge and efficient storage device, and we will talk about like different stages. Okay, So I just borrowed this slide from this link. So most of my slides are like, all of my slides are kind of borrowed from somewhere or the other, right? So all the sources are mentioned there, and you can just go and take a look at it. Okay. So again, this is one pipeline. Okay. So many people must have seen like, a lot of different types of pipeline, but this is from a data or the storage expert's point of view. Okay. So when you look at like, AI as a whole pipeline, you can see like, you get like all this data collected from all your customers or whatever it is. Okay. So first you do data cleaning, then you do feature engineering, then you do actual model training, then you evaluate and tune, and there are like, feedback loops here. And ultimately, once that model is ready, you put it for the inference so that you can get some insights and build some business value out of it. Okay, just training the model is not useful. You should be able to use that model for some real business case, right? So it will feed in some production data, such as I was saying, like some current data, and based on the trained model, you will have some business value coming out of it, right? And ultimately, it will go to the archival stage. So now, if you look at all these phases, and I think like most of you are much more like conversant with all these terminologies than me. Okay, and many of you might be a expert already. So all these different stages require completely different kind of storage device, storage capacity. And when I say capacity, I'm not talking about really the storage volume, how much it's available. Most probably, like whatever data you have, let's say some 10 petabytes, you'll have 10 petabyte storage. Okay, but if you look at the kind of processing or the kind of operations you are doing and the accesses that you are doing, those are completely very different. Okay, so in that scenario, the expectation from the storage device, apart from storing the data, is like whether you are able to do a really fast sequential accesses, whether you are able to do really fast random accesses, whether there are some caching mechanisms available, whether you support large number of parallel requests to fetch parallel data from parallel devices so that we achieve really high throughput. Okay, so each and every phase essentially tells me a completely different requirement from the storage point. Okay, so storage space is one part, but certainly the kind of operations I'm going to perform on that data will determine how I'm going to access that particular data, whether I'm just going to store the data or I'm going to read the data and then store back the results, or I'm going to randomly do both, store as well as load, right? So all those things require different level of performance from the storage device, and hence people tend to use probably different sets of devices to store the data. So for example, data archive, I don't want to store it in like flash kind of device, right? So probably I can store it in some tape drive because I'm not going to access that particular data very frequently. But if I want to do model training and checkpointing and all, so probably I need to do a lot of IO operations, whether store or like load. Okay, and it will be in burst. So for example, many people may not be very conversant about this checkpointing process. Okay, so I think everybody knows the remaining parts, but I think within training, as you are aware, the training activity is not like you can do it in a couple of minutes or hours or days. Probably it will take months, right? And you are doing it on a massive machine. When people are training these like large language models and stuff like that, you must have seen like they trained it on 24,000 GPUs. So now Elon Musk has like 1 lakh GPUs and so on. So when you are running this simulation on the this training operation on the massive scale, you may have a lot of failures in the system, because now when you talk about 1 lakh number of GPUs, there are millions of smaller components which make this huge machine. Okay, there are different DIMMs, there are network attached cards, there are network cables, there are power supplies, there are this, that, right? So all these different components have their own mean time between failures, right? So what happens is, that if I have a mean time between failure for a given device as a 1 million hours, and if I have such 1 million devices, what essentially it means is statistically speaking, every hour I may have a failure. Okay. So in that case, if I want to run my simulation for a couple of months, it's impossible, right? So what we essentially do is we tend to find out this, probabilities of the failure. If I know, there is a probability that I may have a failure somewhere in every 3 hours, let's say. Okay. Then what we typically do is we run the simulation for, let's say, 2.5 hours, and store the current state, so that if there is a failure and if my job crashes, I should be able to restore the job, okay, to the last store state, and I can continue, right? So that is called as checkpointing. And the key problem with checkpointing is it bursts out huge amount of data. Okay, so essentially what is checkpointing? Whatever you have in your a job in a process, everything is stored as a process state, and when you want to restore it, you bring back the state and you continue the program or the simulation or the training, right? So this checkpointing is nothing specific to AI operation as such. Okay, it's specific to these large data centers or HPC systems where you have a long running jobs on a massive system where the number of components is in in large number. So the mean time between failure for the full system for some component in that system is in couple of hours or couple of days. So on such machines without checkpointing, you cannot run large jobs. And in early days when people started realizing these problems, but some people had already built those machines, the problem was really severe, where you do checkpointing every 2 hours, but your checkpointing will take 3 or 4 hours to perform, right? So 2 hours compute, but checkpointing takes 3-4 hours to just store, because your storage was too slow, your network was too slow, and storing and restoring was very slow. So that's why this checkpointing has become a key point in running massive jobs, and especially for AI kind of workloads, when you do it on a massive scale. Okay, this becomes very important, because now if you are running something for a couple of days or a couple of months, and just before it finishes, if it crashes, then the amount of money that you spent in doing the simulation or training is just gone, right? So for example, you must have seen a lot of these startups are getting billions of dollars in funds from a lot of these cloud service providers. Okay, so typically those are not cash awards, those are compute credits. So me as a startup, I'll get, let's say, 100 million or $1 billion worth of compute credits. I'll run my model training operation on the cloud. Okay, and that's the investment coming from that cloud service provider. Okay, so I'll give them equity, because they give me that particular compute resources, right? So checkpointing becomes a very important factor here. And again, inference, as even though the inference may not require a lot of computational time, but to hold the trained model in the memory, you need multiple GPUs and so on. So point being, at different stages of your AI, you need a different type of storage performance. Okay, capacity is one part, performance is a very different part. And hence probably if you just go and talk to a storage vendor, probably and if you have different teams focusing on these different modules, okay, they will have very different expectation from the storage device. And probably the vendor might suggest n number of different storage devices for the same pipeline, even though the data on which you are going to work on is about the same, but probably you will end up having multiple storage devices. It again depends on at what scale you are doing and so on. But for everything, you cannot use the highest possible performance storage. Okay, that's the key point I want to drive here. Okay, so that's why storage for AI in and itself is a very vast topic. And because we are in this particular uh, AI era, I don't want to miss on this part, so that's why I specifically covered this particular use case. If you are interested in learning more about this particular thing, Okay, I tried to briefly cover it, but it's already covered in detail in this particular link. Okay, you can just follow the link. Okay, so now, I talked about a lot of the use cases from outside. So I'll just briefly talk about one of the project I worked on at IIT Bombay. So we did a proof of concept for one of the OEM, right, a couple of years ago. So the problem for storage OEMs is as I mentioned it here, right? So different problems or different applications have different use cases or different types of requirements for storage. Okay, but in typical HPC machine, you don't really have a separate storage device for separate application. We have a common storage device that somebody has bought it, and now that HPC machine or the data center, whatever you call it, it's going to be there for next 4 or 5 years. We are not going to throw away every time NVIDIA comes up with the new GPUs. Okay, probably we may add like newer GPUs, but storage there is a certain lifespan, and it's going to be there. And for GPUs also, whatever GPUs you have bought already, they are going to stay. Okay, plus you are going to add some new thing. So the thing is once I have spent money on the storage device, I'm not going to just throw it away after 6 months or 1 year or 2 years down the line. I'm going to use it for next 4, 5, 6 or whatever number of years I'm going to have it, right? So in that case, and typical HPC machine or the data center need not to necessarily have only one type of application. Okay, so for example, we talked about SCA, we talked about SIR. Probably there we know the application which we are going to run, and that is the only application they are going to run. But when you look at a typical national labs or even Param supercomputers here in India, or a lot of large supercomputers across the world, or even cloud service providers, we don't know what kind of applications people are going to run. Okay, somebody is going to use for weather forecasting, somebody is going to use for some safety simulation, somebody is going to use it for AI, somebody is going to use for something else, and so on. So now for every application, I cannot have a very different storage device, okay, based on the requirements of that particular application. So we do have a tired devices, which I'll cover in the next slide. But the point is, as a OEM of this particular storage device, OEM wants to design a solution which is fairly useful across different applications. At the same time, they don't want to drive the cost too much. Okay, so they don't want to sell you the highest possible application, because then it will be out of your budget, or within your budget you can fit only small amount of storage space into this. Okay, so they will have to come up with indigenous solutions where they can have a very interesting or very intelligent storage device, which will kind of tune the performance of the storage device based on the kind of requests which are coming up. Okay, so I'll give you a very simple scenario. When I'm running a HPC machine, generally there won't be only one application running on this machine. There will be n number of different applications run by different users for different types of jobs. Okay, one might be doing some molecular dynamics, one might be doing some CFD, weather forecasting, whatever. Okay, and beforehand I don't know in which sequence and when different guys are going to run which applications. Okay, so as a storage device, I don't know what kind of requests are going to come to me. Okay, so when I am as a, let's say, a intelligent storage device sitting, okay, and satisfying the user request, it's just that okay, so whatever request comes, I'll just take and give the response, take the request, whether it's load or store, accordingly I'll just be here. But if I can come up with some mechanism by which I can forecast it, or I can create a simulation scenario where, based on a historical data, if I know what kind of applications typically this particular customer uses, and there are different groups of application based on their IO access patterns. Okay, if I can do those groupings, probably I'll be able to efficiently forecast and efficiently service the requests that I'm getting in real time. And what kind of requests I'm going to get in real time, nobody knows, because it's all random. People will submit their jobs at random times. So that is also not guaranteed. And within this particular job also, or the application also, how frequently somebody is going to read and write the data, that also is not known to the system administrator or the system guys, right? Not even like, the storage device. So the user might choose to like, store the data every now and then, or very rarely, or he can just dump like huge amount of data like, very frequently. Okay, so what this does is like, when you run your application in the HPC machine, and there are like other applications which are also running simultaneously on that machine, even though computationally they have like, separate servers associated to them, but ultimately the storage device is one, and everybody is storing the same device. And when you are doing the IO request to the device, it's all going through the same channel. Okay, so everybody is sharing the bandwidth going to the storage device, and we don't know how frequently people are going to ask for like, load or store and those kind of requests, and how much, how frequently. So those are like, very like, real time numbers which we cannot predict. But as a storage vendor, can I do some kind of forecasting or some kind of like, data collection, so that when I build my solution, or when I deliver a solution where like, nowadays everybody wants to like, put in AI into their device or their software or whatever. So can I put a AI into my storage device so that it can forecast my uh, IO patterns, or frequency, how frequently I'm getting certain reads or writes, or like, situations like that, so that I can deliver much better performance to my customers using the same hardware. Okay, so that's the whole idea. Okay, so what we have done here is, as I said, like, we did a proof of concept for this whole pipeline. So we collected this IO logs. So when the job is actually running, there are these tools. So one of the tool that we used was Darshan. So there are like multiple tools which you can use. Okay, so you can collect the actual like, IO operations going to the storage. You can take that log. At the same time, you can collect all these network packets which are flowing through the network, and you have, of course, the job submission information. So what you do is you take all this data, combine it, okay, and sync it up based on the timestamps and store it. Okay, so that I get a real-time picture of the system. Okay, when I'm running certain applications, certain set of applications, and based on that thing, what I can do is, okay, so when I want to design a storage system, okay, I can replay these particular logs or aggregated data, or I can run the simulation. Okay, so why do I need to simulate it? So now let's say if I have much bigger machines than what I collected on, right, then the amount of data is be much higher. So I should be able to simulate much larger machine, and like, applications doing much frequent accesses, right? So you have multiple like, parameters which you should be able to like, tune and tweak and play around, and that's how you actually do it. So the idea behind doing this POC is like, how do I design a system which is cost effective, okay, at the same time delivers the higher throughput. Okay, again, within the storage like, device, there are a lot of different components. How do you store, like, there are these caches and so on. Okay, so we don't have enough time today, so I didn't like, really cover a lot of the things, and I just put up a like very simple diagram here. But the point is, if I have that information, I can really build a really interesting and really efficient platform. Because see, the thing is, the point is, when I typically go and buy a car, right, so I know like, there is a mileage, okay, 20 kilometers per liter or 15 kilometers per year. But that's an ideal scenario. You may or may not get that kind of mileage. If you're a really like, nice driver who like, is like light food and so on, probably you can achieve. if you have a really hard driver who accelerates hard and drives at 150 kilometers per hour and so on, those kind of thing, probably you are not going to get that kind of mileage. Same thing with the storage device. So when you buy a storage device, it comes up with some specifications. So this much storage and this much amount of throughput you can get and so on. But in real life scenarios, throughputs can be really bad. And in fact, if you are interested, I can share a paper where people talked about really massive machines where some of the applications getting 1 mbps, 10 mbps kind of write throughput. Okay, because the access pattern was really bad, and it was being done at a much massive scale. Okay, so effectively, even though there was a high bandwidth to the device, there was a high capacity, there was a high throughput capacity of the device, it was not able to deliver that kind of number, right? So that's why the storage devices, even though they are kind of silent in the HPC machine, but they play a really crucial role here in this HPC machine. Okay, so broadly, I will just sum up this slide. Okay, and then I'll stop, and then probably you can take up some questions. Okay, I hope I'm on time. Yeah. So if you look at a traditional HPC machine, there are n number of different types of storages for different purposes. Okay. So for example, if you want to just store the software, okay, install the software packages which people are going to use. Okay, so it need not to be really large storage space, few tens of TBs is enough, because you are not storing the actual data. Okay, you are just storing the software. Okay, but the storage lifetime is long term. Okay, and people can share the data. Okay, again, we didn't talk about sharing policies and security aspects of that part, but yeah, so people can share the software, right? The IO throughput need not to be really high, because it will again increase the cost of the machine. Okay, and you are not going to read write this data very frequently. Once in a while, or initially when you launch the application, probably you are going to read a lot of the data, but otherwise you are not really concerned about how fast you are getting the data from this particular sub device, or a storage device. Okay, and idle latency, I don't really care too much. Okay, if it is a low or high, I don't. So okay, and mostly I'm going to read, I'm not going to read and write. Okay, mostly this data is going to be read. Okay, so once in a while, certainly we are going to install the software. Okay, but the point is, mostly it's the use case is read. So now if I ignore the remaining rows, and if I just focus on this thing, okay, and I'll just go and approach a software storage vendor, he'll give me a certain storage device, okay, which will be optimized on price as well as my requirements. Okay, because cost is very important here. Okay, but this is specifically targeted towards storing the software. Okay, I don't really care if it can be also used for other things. So sometimes if you have a small machines, and if you don't have large budgets, probably you'll buy one fits all solution and just use it across all the things. If you are a large facility, probably for every such a row, you will have multiple storage devices based on the key requirements, and it will optimize for the requirements as well as the price point. Okay, the second row here is the user home. So our typical home directories, where we store the simulation outputs, okay, which will be medium term. Okay, so there are these two things. Question. Okay, there are these two things. One is called as user home, okay, and scratch, and certainly there is a project home where people can share the data.
First PhD
Question. Okay, sorry. Yeah. So the user home and project home, the key difference is user home, it's specific to user. Project home is shared between the users. And okay, so this thing you can club it together for sake of discussion. But there are these two key storage units, whereas one is user home or project home, and one is scratch. So what is the difference? So user home and project home, they are medium term storage units. So whatever I store in my home directory, okay, that's I'm going to consume it over the period of time. Whereas scratch is something, when your job is running, you are not really storing the output to the home directory. Typically, you will write it to the scratch, and when your job is complete, you will move it to the home, right? Because again, the point is, if you read through these lines, it will be very clear. Okay, so user home will have a higher capacity as compared to scratch. Okay, and the storage lifetime is also much higher. Okay, but IO throughput need not to be really high, whereas for Scratch, it needs to be really high throughput, and the latency should be also low. Whereas for home directories, whether it's a home, user home or project home, it need not to be really high, specification storage device. So medium IO latency, medium throughput is okay, but Scratch is something which is the highest performing storage. Okay, which may or may not be very large, but essentially it's a very short term storage. And generally, if you look at a lot of these HPC sites, they will have policy like, whatever data you have in your scratch, okay, they will delete it after like, 7 days or 1 month after your job is complete. So it's auto delete. Whereas your home and user home or project home, it's there as long as your account is there. But scratch, they will keep deleting because a lot of people are using the scratch which is being shared, because this is the highest performing storage. Okay, so here it's being shared. Okay, and it's really high bandwidth available. Okay, high throughput available, and latency is also very low. And this generally allows both read as well as write. But here home directives are generally mostly reads, right? So we will not be doing a lot of writes to home directory, because all the data which I'm going to process or generate sits in scratch when the job is running. When your job is complete, we'll move the data back to the user or project home. Okay, and finally the archive, I believe everybody knows, like, tape drives and all, like, probably you can have really large capacity. So we talked about exabytes of storage and all, so that people are not going to use it like, day in day out. Okay, so you can put it in some disk storage, and generally they have like, large archives in terms of tape drives and stuff like that, because it's way cheaper than having really high performance storage. So I can, like, if I'm really rich, I can have a scratch for exabytes of storage, which will give me like, really high throughput and low latency. But then essentially you will be spending most of your budget on the storage device, and you will not have money for buying the actual compute server or the network, right? So that's why these are like, few categories, but depending upon the complexity of your machine, like different storage devices are designed and installed with different capacity and different performance requirements. And certainly I didn't really talk about different types of storage devices, okay, because our focus was towards like an application. But there are different types of devices. I briefly mentioned about like, flash or tape drive, but now there are new technologies also have come up at the software level. Okay, whether it's object storage or parallel file systems and so on. So depending upon the requirement, you can use these different types of technologies, which will in turn use different types of storage devices depending on the requirement. Okay, so these are like, typical ways people tend to build the storage into the HPC machine. Okay, so I think I've like, already covered a lot of steps. So these are like, some of the links for more details. Feel free to reach out to me. I can share more details if you have any specific queries. I'll stop here, and if you have any questions, we can take those questions. Yes.
Yes, sir. There are few questions in chat box from the
Yes, ma'am.
participants.
Yes, ma'am. Yes, ma'am. So, okay, sorry. So I'll stop presenting so that yeah.
Uh, Participants,
Okay, I don't see. I don't see it here, ma'am. If you
if you
see,
have any
can
kind,
you?
yes, sir, yes, sir.
Yeah.
Participants, if you have any kind of doubt or question, sir is here. Please feel free to ask. I guess there are no more questions from the participant side.
Sure, ma'am. Yeah. So I think it was like, too fast, and I tried to cover a lot of stuff to the slides. And anyway, sir also covered a lot of interesting stuff. Yeah.
Yes, yes.
So, yeah. Thank you.
Thank you, sir. First and foremost, I extend my deepest gratitude to Dr. Pramod Maske sir and Mr. Mandar Gurav sir for gracing us with their presence and sharing their valuable insights. I would also like to acknowledge and express our thanks to all the attendees. Your presence has made this session all the more meaningful and memorable. Thank you all, and we hope to see you again at tomorrow's session. Ma'am?
Thank you, ma'am.
Yes, yes. Thank you, sir. Thanks a lot for joining
Yes,
and
thank you.
your informative session. So now Pramod Maske sir, I think he has left. He has another meeting.
Yeah.
But
Yes, yes.
Mandar sir, thanks a lot for this informative session.
Yes, thank you, ma'am. Sure.
Thank you, sir.
Yes, thank
All
you,
the
ma'am.
participants kindly fill session 1 and session 2 feedback form, and then you can leave. Sir, so we'll stop
Yes,
here
thank you, ma'am.
for today's presentation. Okay,
Okay,
sir.
yes, thank you, ma'am.
Okay. Thank you,
Thank
sir.
you all,
Thank you.
and
Thanks a
good
lot.
night. Yeah, thank you.
All the participants kindly fill the feedback form, and then everyone can leave. And thanks a lot for joining today's all the sessions.